Hello students, welcome to this lecture in which we're going to talk about surface integrals. Before we talked about flat lamina to get the integral, but now let's think about a curved lamina. Right, so it's very thin object. We can think of it as a bent plate. That encloses 3D surface like an eggshell. Alright, so suppose we have this lamina and suppose the top of it is dark blue. So basically we will have something like this. Something like this. So suppose the top is dark blue, so this top is dark blue and the bottom is a light blue. So here we can see the bottom here. So it's like it's bent around. And if we look on it from the top, then we will see something like this. All right, and it's bent. So if it subdivide, let's give it a name first. So we have a curved lamina, and we can model it. We can model this lamina by a smooth didn't spell it right, smooth parametric curve. I said curve, it's not really right. Parametric surface, let's call it sigma. And given any point x, y, and z on the sigma, we let f of x, y, and z denote the value of a density at point of a density function. So what is the mass of the lamina? That's the question, like we had before for the flat lamina. So to do this out, we just need to calculate the mass. So what we can do, we can subdivide this lamina into the subregions, right? So we can go and do this, and it's bent, so it's not straight lines. So they go on the surface and they bend. Right, so something like this and something like that. All right, so if I think about one piece over here, all right, so what can we say about this piece? In the middle, our famous point, x sub k star, y sub k star, and z sub k star. Right, and then this piece itself we can call delta k if we subdivide into the region. So we divide sigma into small patches, sigma 1, sigma 2, dot dot dot, sigma n. And each one has an area, so with areas s sub 1, s sub 2, dot dot dot, s sub n. So this piece has an area s sub k. I said s sub k, that's not really right, so let's call it, we usually call them delta s sub 1, delta s sub 2, delta s sub n, so this will be delta s sub k. That's a better notion. All right. So we can approximate all of the values on this bent page by this value over here if we evaluate f at this point. All right, so we can approximate f on the page sigma sub k by f of x sub k star, y sub k star, and z sub k star. So all of the values around it we can think of as the value at this point over here. So what does it mean for us? Then that means that if we take delta m sub k, which is the mass of this particular page k, right? So this is the mass of a page delta sub k. Sorry, sigma sub k. Didn't call it just right. So how can we approximate it? We can approximate it by taking the value here, which has all of our x, y, and z, and multiply by the area of this page, which is delta s sub k. Then to get the mass, we just add them up, right? So therefore, the m is approximately no, not m is the sum of all of this delta m sub k when k changes from 1 through n, and we take delta m sub k. And each one of them is approximately this, so it's an approximately the sum when k goes from 1 through n of f sub, not right, f of x sub k star, y sub k star, and z sub k star times delta s sub k. All right, so the only thing left for us is to take n and send it to infinity. So to get the actual m, we take a limit when n goes to infinity, sum when k goes from 1 through n, f of x sub k star, y sub k star, and z sub k star times delta s sub k. All right, and so we know what this means, right? This is exactly the definition of the double integral. This is exactly the definition of the double integral. So let's write the definition. So we can say that if sigma is a smooth parametric surface, then the surface integral, and that's what we're trying to define, so I will underline it, of f of x, y, and z over sigma is given by the integral, right? So we say the double integral over sigma f of x, y, and z ds, which is equal to the limit of this quantity, right? So n goes to infinity. We have a sum, and k goes from 1 through n. We have f of x sub k star, y sub k star, and z sub k star times ds sub k. All right, so what we need to add, the limit should exist because it's not always true, so we have to say provided the limit exists, the limit exists, and does not depend on the way that we subdivide the region. So any kind of subdivision should give you the same answer. Does not depend on the way the subdivisions are made. Or how we choose x sub k sub star, y sub k sub star, y sub k star, and z sub k star. All right. So that's our definition, and so let's move a little bit further. Okay, let's move a tiny bit further. So, so let's call this definition star. Let's call this definition star if we need to use it later. So if we think of f as a density function, so if f of x, y, and z is a density function, then the mass is given by, so we can find the mass by taking this integral over sigma of f of x, y, and z ds. And small note that if f of x, y, and z is equal to 1, then the area of the lamina can be calculated as double integral over sigma of ds, so it's 1 times ds, so I'm not going to write 1, so just ds is equal to the limit when n goes to infinity of the sums of k equals 1 to n of delta s sub k. Basically, it just sums up all of the sums of all of the areas. Sorry, all of the areas, right? So it's going to be the limit of s, because we added up all of the areas. We got s when n goes to infinity, and this is just s. Okay, so basically we can calculate s by taking the double integral of 1 times ds, and it's the old formula. We had this before. Alright, unfortunately this formula star doesn't really give us good way to calculate the answer. This is kind of very general, not really easy to calculate. So let's see how we can actually use this formula to evaluating surface integrals. That's the next topic, surface integrals. So how do we evaluate surface integrals? So unfortunately there are many different ways to do that, many different ways to do it. One way is the following. So one way is the following. Because it's hard to represent the sigma, so let's take one representation and see how it will help us. Let sigma be a smooth parametric surface, whose vector equation is given by r of r is equal to x of u and v times I plus y of u and v times j plus z of u and v times k. So basically it's not really a line, it's a surface. So if we want to represent surface, we need two parameters for each x, y, and z, and this would be u and v. So where u, v varies over a region R in the UV plane. So we create a UV plane in which we move around. So if f of x, y, and z is continuous on sigma, then let's try to think. Then the double integral over sigma of x, y, and z ds, so it's starting with our formula star, can be represented as this integral over this region R. And so for x we put this quantity, so it's f of x of uv. For y we put this quantity, y of uv. For z we put z of uv. And then I'll put a strange thing over here and we'll talk about it, why it's true. So basically what we can do, we can put the lengths of partial of r with respect to u cross partial of r with respect to v ds. So what we do, we go back to this piece over here and And if we grab it from here to put it below, okay. So let's try to put it here. All right. So if we so let's try to think why this piece here. So basically we can take each of these pieces and we can construct a little parallelepiped over here like this, right, and approximate the area on the surface by this parallelepiped, where these two vectors here would be, these two vectors over here would be partials, right? And we know that the area of this parallelepiped is the magnitude of the cross product. All right, and so that's how it comes up. All right, so we approximate this, and here I made a mistake, this should be dA. All right, so that's our standard rule, but we just add this piece to approximate the area over this ds sub k. And that's how it came up. That's how it came up. That's the derivation of this formula, not the full derivation, but just explanation how this formula comes up. So all right, so in the next lecture we will continue with examples. I think I'll stop this lecture over here. So examples will come in the next lecture.